So for this next exercise, we're actually going to continue thinking about this framework as we just described it. So what are your TCO, time at risk, and your outcome model? And in order to do that, now we're actually going to look at somebody else's study. So as homework, you all had to read the paper by Graham and colleagues. Sure you all did that. And we also handed out copies of the paper. So I hope everybody has a copy of the paper. So the reason why we gave you this paper is that we actually think this is a pretty good paper. It's a good example of how one goes about doing comparative cohort analysis. Maybe some things could be improved, but maybe we can get back to that later. But what I want you to do is to team up into groups of 4, so maybe your neighbors and the people behind you. And then as a team, go through the paper and try to identify your target, your comparator, your outcome, your time at risk, and the model that they're using. So read the paper, or you should have already done that, and identify those 5 components in the paper, and then we'll circle back and try and see if everybody was able to find that in this paper. All right, go ahead. All right. So what do we think? Did everybody succeed in fitting it in our 5 questions? All right. So let me hear. What is the target cohort in Graham's paper? Any volunteers? Nobody? All right, go ahead. Yes, please. Don't be shy. So what was the definition of the target cohort in Graham's paper? Sorry, who said that? Patients taking dabigatran. Yes. Yeah, dabigatran. Yes. So was that the cohort definition? Or was there more to it than that? So patients in Medicare. Yes, patients in Medicare who with AFib who are new users of dabigatran. So starts to sound good. Was there more to it than that?
Who are also 65 years and older.
Old.
And were enrolled in fee-for-service Medicare Part A, B, and D for at least 6 months.
Yep, 65 years or older and enrolled in those various parts of Medicare. I think there was even more to it than that, right? All right, not gonna keep people in suspense. I wrote it down somewhere. So they had what we call a bunch of inclusion criteria and exclusion criteria. Maybe important to point out that as we start to work with the OHDSI software, there is no distinction between the two because you can turn an inclusion criteria into an exclusion criteria in the other way around. So we just have inclusion criteria, and if you want to exclude people, you just say people who don't have this. That's then your inclusion criteria, which is excluding people. But anyway, so Graham said, well, they have to have an inpatient or outpatient atrial fibrillation or atrial flutter, sorry, ICD-9 code. They had to have filled at least 1 prescription for one of the 2 drugs. And the index date is the first prescription date. So those are the people that go into the target cohort. And then they had a bunch of exclusion criteria. So you had to have at least 6 months of Medicare enrollment before the index date. And else you're out. So why do they require that? Anybody have an idea? Why require 6 months of observation before they start the drug? Baseline covariates, yeah. You want to know something about these people because you want to know if they're comparable. And you can only get that from the baseline period, so the time before the decision was made. Why 6 months? Well, that's a good question, and actually I don't have an answer for you. So I think this is one of these things where it's just everybody does the same thing because everybody else does the same thing. So you typically see 6 months or a year, but there's no hard, fast reason why. Oh,
I would say, though, that if you, part of your inclusion rule is saying that you must not have something in the prior year or 6 months, you cannot assert that something did not happen unless you observed it. So while you said, I could say 3 months, I could say 4 months, if there's a rule that says did not find it in the last 6 months, you should have your prior observation, the minimum of any look-back period that you're looking for the absence.
Yeah, but that's true, but that has to come in your first criteria, when you say what is it that you're looking for in those patients. So let's say if it's an incident, then you can say, I would like to know for sure that the index, whenever the prescription is this patient didn't have anything before, and I need this prior period of time. That's very good. Not if your question would be, how many patients having this condition started to take this medication? The enrollment criteria becomes a period of time that you choose depending on whatever you want, because it's not anything based on anything. A patient could be in a commercial plan, become Medicaid, have the same disease, and start just to take a medication. Does that make sense?
yeah, yeah. So there is.
So what it is, what your question is, if you would like to know the patient in a particular time, and you like to look exactly when they start the prescription, and your criteria doesn't include anything related to, let's say, it's first time, it's an incident, whenever they were Medicaid, there is no reason for this exact period. But if you have the criteria, that specificity, if you want to know if they didn't take the medication before, or they were enrolled in Medicaid, or, I think that's why the time comes in.
All right, so let me unpack what's being said here because it's a lot.
I said that a lot of similar things for another topic, and I have to go to this exercise. You know, like what we're coming up with the time. You can about 6 months, 3 months, 1 month, whatever.
All right, so trying to unpack all that. So we established one reason for having this observation period prior to the index date is to capture baseline covariates because we want to know these people and make them comparable. Another reason brought up by Chris is, well, if we have inclusion and exclusion criteria that say can't have this in the prior year or something, well, then we need to at least require a year of observation to make sure that that rule is applied correctly, because if we allow people that don't have any observation prior, them saying that they can't have this in the year before, we might actually not have them observed for that time. And then the third point that was being made there is we're looking for new users of this drug. And so if we don't require a certain amount of time of observation, it could very well be that these people were on the Bigerton for a long time, or warfarin probably because it's an older drug. They were on warfarin already for years, and then they enrolled in Medicare, and they just continued what they were already doing, and so they're not new users. And so we're requiring a period of 6 months, and maybe this was the reasoning that Graham used. We don't see any warfarin or Dubicurton for 6 months, and then we see a prescription, then we're probably safe to assume that that's their first go at that drug, the time when they really start taking that drug. So these are all considerations that go into deciding how much, well, first of all, whether you need it, and how much time do you want to be there.
Can I ask a question?
Yep, sure.
About the baseline period. All of these came about before medical record data was used. So if you're using medical record data, and in theory, I mean, you may have an observation period based on when they're covered or not covered, but you may not be able to capture their care even if they are covered, because they could go to a different clinic or something than your hospital medical record database has. How do you see people normally defining 6 months based on medical record data, not insurance claims enrollment data? Do they have to have a visit at least 6 months before, or?
Okay, so this is actually a slightly separate question. So I could be very cut you short there. So there is a table called the observation period table in the common data model, which tells you when people are observed. And so what we're going to do later probably is we'll define having 6 months of prior observation simply by doing a check against the observation period table. But then the question is, how do you populate this observation period table? And so in this case, Graham had it pretty easy because he's using insurance claims data, and there's an obvious choice, which is the time when you're enrolled in your insurance, because while you're enrolled in the insurance, probably most of the things that happen to you during that time in terms of clinical interventions and diagnosis all end up in your record with the insurance company. But if you're looking at an electronic health record, that might actually be a lot harder to decide what your observation period is. And so I've seen people, when they have like a hospital database, if it's a hospital where people go to, but they're equally likely to go like the hospital across the street, then maybe the best you can do is just say the observation period is just the days when they're in the hospital. And then if you start to require that they have to have 6 months of observation prior, then nobody in your database will satisfy that unless you have some very odd people that actually are in the, well, so we've seen that in the Korean databases. There actually are people in the database for 6 months, but they're a very special group of people. So actually some of these analyses you couldn't do in an electronic health record system simply because you don't have the full observation period. But so per database, you actually have to decide on the rules that you use to set the observation period. And so some like health research networks actually, they cover a whole region, and if anybody in that region goes to the hospital or the clinic, that will be captured. And so you can say, oh, I'll start at the time when I first see any diagnosis or prescription, and I'll stop when I'm either dead or I don't see anything anymore. And that's my definition of the observation period. But I'm trying to point out that's actually a separate discussion in terms of OHDSI, how you define your observation period, and here how you use that observation period. Yep, go ahead.
So I think so people will become eligible for Medicare when they are 65. So if they are just including patients who are more than 65, is there any enough observation time, background observation time of 6 months before for them? But I have seen papers using Medicare that they restrict to people like 66 years old, so they are sure that they have at least 1 year background baseline observation time before, but in this case, people just are newly enrolled in Medicare.
Well, so that's a good point. So they're saying you have to be older than 65, and you have to have at least 6 months of Medicare enrollment, and pretty much everybody in Medicare starts to be enrolled when they turn 65. So you can already see that probably that second restriction isn't all that important, except I happen to know that there are some people that are already in Medicare before their age of 65 if they have a serious chronic disease or something. Yeah. But most of the people in this study will be 65 and a half years old when we start to include them, because we already require them to be at least half a year enrolled. So we could also just have said they have to be 66, but then there are people who maybe enroll in Medicare when they're 66. So at least requiring them to already have that half a year of enrollment might actually filter out more people than just saying you have to be 66 or older. All right. I think that's a typo, right? You have to be older than 65.
It's an exclusion.
Oh, it's exclusion. Oh, sorry. You exclude people. All right. So they're excluding people who received the prior treatment with another novel oral anticoagulant or warfarin. So why are they excluding those people? And why are they looking for new users? Would you happen to have an idea? Sorry?
I would say the difference in it is that it is the nursing facility should be patients who are.
We're doing the prior bullet, right? So
Yeah.
anything about the warfarin? No.
Yeah. Why no prior warfarin? Yep. That's That was the answer I was looking for. You want to establish causality. So if they're already on another drug, one of these two drugs for a while, and they're now starting on this, well, how do we know it's because of this drug or another drug? So we want them really to be clean relatively, and then they start taking the drug, and then we can see what happens after they make that decision to take that drug or the other drug. So they exclude people that are in a nursing facility on the index date. So again,
Very severe cases that were biased, the findings.
severe cases because they're biased. That might be one reason. I can think of another one, maybe.
I think directly related to the outcome.
Or in many cases, we may not observe exposure to people.
I think probably that's it. Like people that are in a nursing facility, like they have their own pharmacy, and you might not actually see everything that happens to them in your claims database. I'm guessing that's it, but it could also be that's a very severe population that you want to exclude. I don't think Graham said at all why they did that. It's also always interesting when you read these papers, there are so many decisions being made and they never tell you why.
That's also like a standard decision. Everybody excludes, those who are in a skilled nursing facility
Yeah.
without asking why.
Yeah. It's again, it's the thing that everybody does, so we also just do it. I don't see, so usually you exclude people with cancer as well, right? That's just, they exclude people that had a hospitalization that extended beyond the indexing dispensing date. So that means that they were already in the hospital and then they got the drug while they were still in the hospital. I'm guessing that's pretty much the same reason, but probably maybe a sicker population that you don't want included. But also, again, you might not observe everything that happens during the hospitalization, or certainly maybe not. You don't know the exact timing of when that happened. Like stuff that happens in the hospital, like a new thing that happens while you're in the hospital, does it show up as in your discharge record or So they exclude people that are undergoing dialysis. Did Graham specify when? Oh, go ahead.
That changes the metabolism of the drug.
Probably, yeah. That's a good point.
The results of the drugs, they have to adjust the doses, and then that will exclude them because the other patients are taking some of the doses.
Yep. Probably the same reason why they exclude people with kidney transplants. And then they have other diagnoses that they're all excluding in the 6 month baseline period. Because these criteria, might be important to point out, they applied exactly the same criteria to the target and comparator cohort. So the only difference between the T and the C was the drug that people started on. And actually, as you design your own cohort studies with our OHDSI tools, you will often find that what you're doing is you're designing your target cohort with all the inclusion and exclusion criteria. And then you just copy that cohort, and then you just swap out the initial index event that you had defined to create your comparator cohort. All right, going to the outcomes. What were the outcomes that Graham and colleagues are looking for?
Diagnosis of bleed, so AMI, gastrointestinal bleed.
Yep. Was it AMI?
Yeah.
Okay, so you're right.
Specific focus on interferon, gastrointestinal bleeding, and AMI.
Yep, and I think they had mortality in there as well, just plain.
Secondary.
Yeah.
Is that a primary?
All right, so did they give definitions for those outcomes?
Yeah.
I think it's in the appendix, right?
IC9 codes, table 2.
So,
Oh, but a code set.
yeah, a code. We just said a code set is not a cohort. So you see this a lot. I think they're just being, they're implying something, but they're not being explicit about it. So what would be the cohort entry date for the stroke cohort? Are they? Do they define the logic by which you translate this code set into a cohort with an entry date and an exit date?
Can we just use the same dates as the initial event?
Yeah, that was a question we haven't argued, but we can quite find it.
The initial event, sorry?
October 19th, 2010 is when the prescriptions have to occur between. So could you just say that the study outcomes are starting October 19th, 2010 and then going through the study period?
But that's not the date when you have the stroke, right? What is the date? Do they specify how you find the date of the stroke?
Well, it'd be the first day that you observed it in the first position, right? In the inpatient setting.
I'm pretty sure that's it. They didn't make that explicit.
So it's any time during the study period having one of those.
Yeah, having one of those codes in, I think, in the primary position is what they specified. So that could have been a little bit more explicit there.
That they say the primary, if you actually read the validation studies that they reference, they say, papers, they say not to use the primary position. There's a little disconnect. Not to use the primary position.
Yeah, we'll actually get to that later, but they do have some justification for this outcome definition, and if you actually look at the reference that they give, then that paper says not to do what they do. But that's it's a separate point. All right, time at risk. I think this was a hard one for most people. What was the time at risk, as Graham defined?
Until they disenroll from Medicare, is what they actually said.
Starting from the day after the index event.
Starting from the day after the index event. What was the index event?
First prescription between.
First prescription. Yeah, so starting the day after they got their first prescription, or started on probably their first prescription. That's the start of the time at risk. What was the end?
There's a whole bunch of sensory events they list.
Sorry?
There's a whole bunch of sensory events they list here.
All right, can you name some of them?
Okay. So it's disenrollment from Medicare, occurrence of a study outcome, end of study period, a gap in anticoagulant, days of supply more than 3 days, a prescription fill for a different anticoagulant, initiation of dialysis or kidney transplantation.
Very good.
To a skilled nursing facility or nursing home, transfer to hospice care, whichever came first.
All right, very good. So I think I listed most of them here. Actually, probably the most important one is that second one, 3-day gap in anticoagulant supply. Because if you're taking the drug and you get one prescription of, I don't know, what's the usual length of prescription for warfarin? 30 days, 60 days? If you get that prescription and then you don't get another one, you're already out after 60 days. If you get a new prescription, it has to be within 3 days of that old prescription running out, or you're out. So that's pretty restrictive, and probably, as you probably would see in their data, they lose a bunch of people already pretty quickly, and then a lot of people, of course, also stay on the drug for a very long time. So they also stop following people up after they switch to another drug, probably also for causal inference reasons, a good idea. Medicare disenrollment, of course, if you're no longer observing people, probably a good idea to stop following them up, and some other reasons. One important consequence of this is that, as I pointed out, there's actually not a fixed time window when you're observing these people. So some will be in there for 30 days, maybe 60 days, and some will be in there for 10 years, just because they stayed on the drug for that long, and we were able to follow them for that long. And so in that case, we can jump right ahead to the next question. What was the model that they used? What kind of model would you use if you have data like that, where people have all different types of follow-up time? Cox proportional hazard. Yeah, that's the one that makes most sense here. Didn't actually write that down. All right. So they use a Cox proportional hazard model. That's right. Yep. All right, let's see how we're doing on time. A little over. All right. So now we're going into some more lectures, this time from Alex. Thank you.
James, when he was introducing my part, he said I was going to talk about everything that can go wrong when you're doing an observational study. So, well, spoiler alert, I don't think I can tell you all that can go wrong. Things can go wrong, right? And that's why people have trouble believing in results generated by observational studies. When you have studies like people born in August tend to be happier than other people. The study performed in August, so everyone is happy, they're having holidays, and they had their birthday 5 days ago. Yeah, they tend to be happier than others. So we need to see now what some things that could go wrong. First of all, I want to thank James for ruining my first ever slide as an instructor in all this tutorial, where he talked that we need to design our observational studies like we would design a randomized trial. And I just want to go back to this slide and say that there is a good reason why we need to do that, because there's a legitimate reason why randomized trials are thought to be the golden standard when we're analyzing a research question, because when we're doing a randomized trial, we make sure that the two treatment arms, they are only systematically different with respect to treatment that they receive, and everything else can be exchangeable. So if we see a difference, then we can say that this difference can be attributed solely to that they got a different drug. And so if we try to stick to this, if we try to emulate this approach in our analysis when we're analyzing an observational study, then we can hope that we don't get immediately wrong, and because then things can get very wrong very quickly, right? First I want to discuss about some stuff that I think, so that this, whenever we're doing an analysis, whenever we take a sample from a population, and we want to, even with a randomized trial, and we want to estimate a parameter of this underlying population, there is always going to be some error in our calculation. So even if we have a randomized trial and we sample our population correctly, and then we calculate a treatment effect, if we were to do this thing again, we would get a different estimate, right? I think. And then which one of these is true? None of them, probably. So the hope is that if we kept doing this thing, in the end, all these estimates would end up concentrating around a certain point. And this concentration point, if it was a randomized trial, we hope that this would be the true actual effect that we were trying to estimate. However, when we're doing an observational study, there is another form of error that is intrinsic to our sample. So if we were to repeat our sampling approach, and then we would get another sample and another sample, and then we would estimate again and again and again, our estimates would gather around a certain point, but these points actually might be far away from what the truth is. And this cannot be solved even if we increase our sample size. So this is what the first formula presents. So bias can be just the distance between our false concentration point from the truth. So so whenever we're estimating a certain parameter, then if we want to evaluate how well we're doing, then we need to use some metric like a mean squared error, which is a combination of both our our systematic error and our random error. And the thing is that with increasing sample sizes that we have when we're doing observational studies, we tend to get even smaller confidence intervals around the wrong thing. So we're more certain about the wrong thing. Yeah. So there are 3 major types of systematic error that we want to try and assess here in this talk. So first of all is confounding, second is measurement error, and the third is selection bias. I'm sure that most of you are familiar with all of these, and at some level, or at least. So when we're talking about confounding, so we have a treatment, we want to estimate the effect of this treatment on a certain outcome. But because we have an observational study, then there might be other factors that are systematically different between the treatment arms, resulting. How do you say that? So there might be factors that are systematically different between the treatment arms, but they at the same time affect the outcome. So if we find an effect, we're actually not finding an effect, but we're actually finding the effect of these factors to the outcome. So if I could use an example to make it a bit simpler. So if a certain treatment is mostly given to older people, right? And then older people also tend to have worse outcomes. So in our study, we end up having more old people, and then we may end up saying that our treatment is harmful, but while instead the whole harm can be attributed to the age. So we need to be able to account for all this, measured confounding. So I think James talked about it. So we need to estimate our propensity scores, and then we managed to estimate our propensity scores. Then we managed to account for all the measured confounding that exists in our trial, but in our study. However, there also may be some unobserved factors that affect both treatment and the outcome, which we don't observe. So even if we do everything right, we estimate our propensity scores, we can never be sure that the unobserved confounding didn't end up ruining our result. So the ways that we can assess confounding are either by looking at the propensity score distribution or the covariate balance. So when we look at in the graphs that James showed before, if we see that the propensity score population distributions are very, very much separated from one another, then we can say that from the measured there is some factors that we measure that we can use to predict accurately exactly what treatment is given to which patient. And then if these factors are also can be also associated with the outcome, then there will be for sure confounding in our analysis. So we should maybe stay away from doing any step further. So misclassification or measurement error. So this is the same graph as we had before. But the thing is that because we're doing an observational study, we don't know what we don't have the actual treatment outcomes and all this stuff, because the actual measurements that are gathered were not gathered for the purpose of the analysis, right? So instead of a treatment definition, we have a proxy for this thing. So this could be a set of rules that we use to define treatment. And then we have a set of rules that we use to define the outcome. And then also have a set of rules that we use to define the factors that we suspect that could be confounding the association that we're estimating. So instead of estimating the green association, we end up estimating the red one. Yeah. So this is very. So how can we assess this? How this is often assessed is by doing a covariate summary for the exposure. So, or the second part, which is operating characteristics for outcome phenotype. So we find a set of patients for which we actually know what the outcome was or what the treatment that they received was, and then we use this as a golden standard, and then we estimate, and then we want to see if the rules that we used actually identified them or not. Yeah. Finally, selection bias. This happens when instead of having so this happens when we don't have a random sample from the treatment. From the treatment population. So this could happen, for example, when we're trying to do a per protocol analysis, where we want to assess if all patients, we want to estimate, so we only focus on patients that actually follow the treatment that was assigned to them. So if these patients who were assigned treatment also were more like, had more health conscious, or so they ended up following the protocol while others who were not as health conscious didn't. So we may end up overestimating the benefits of the treatment that we have we're considering. Yeah, now this can be done. So we either look at the attrition table, so we want to see. We can compare the rates at which we are losing patients from each treatment arm, or we can look at the covariate summaries before, as people enter the study and when they're exiting, and then compare if there is a difference between. So if there were certain characteristics that we kept losing throughout the study. So what we can do to address these challenges, first of all, think really hard and hope we get it right, and then be honest about if what we're doing, be honest on what would go wrong. So first thing is think hard on how to do this right, and then think even harder what would be the reason why everything that I did is completely wrong. And the last two parts that we're going to discuss today are how to perform some diagnostic analysis and attempt to see if there is, in truth, some residual error that we couldn't, we didn't manage to capture by doing a propensity score analysis or any other approach that we use to account for systematic error. And then another thing would be to quantify the magnitude of the residual error. Okay. So we start with an example of a study that was performed in 2008 when it was trying to assess the association between the effect of infectious mononucleosis, I don't know if I am anyway, on multiple sclerosis. So people gathered their so this was an observational study performed in a Dutch population. So the researchers there just calculated odds ratios, and then they found out that all of the considered diseases were causing, not causing, it's not correct. Like they were associated with multiple sclerosis, right? And then because they knew that this was an observational study, they said, okay, then what if we use some diseases that we know that do not cause multiple sclerosis? What will we see then? And the thing is that, again, they saw that in their data that also concussion causes multiple sclerosis, or tonsillectomy causes multiple sclerosis. So this showed them that this shows that there was some systematic error that they were not accounting for in their data. So what the conclusion was from this study is that, okay, maybe one is not the right, an odds ratio of one may still be, a little above one may still not be, may not still show an association with multiple sclerosis, but okay, infectious mononucleosis was 2.2, so which is much, much higher, so maybe this is the one that actually is true. But the thing is, what if we considered 100 of these negative outcomes? Then maybe 2.2 wouldn't be so big then. But we don't know because they only consider these three. Or maybe there were more, but we never knew.
Can I ask you, what's the likelihood though, like concussion probably or not, but like what's the likelihood that what you're seeing is not necessarily a confounder for multiple sclerosis, but associated with one of your infections, right? So maybe mononucleosis causes tonsillitis, which means if you have that, you're also more likely to have tonsillectomy.
Yeah.
Yep. All right, so that's a good question that we always struggle with when we define negative controls. So how are you certain that there is no causal pathway from the negative control to multiple sclerosis? And so you just made up you came up with a valid, plausible biological pathway by which actually that could be associated with the outcome.
But the beautiful thing is we do lots of them, so
Yeah.
5% can be okay. I mean, can have something, but like concussion, there's probably no plausible biological pathway, and it's still significant. So
Exactly. So we tend to not rely on one or two negative controls, and we actually usually are very, very strict on what counts as a negative control. And so probably in this case, we would already have eliminated some of these just because of an expert would have to review these and would then maybe rule out some of these negative controls. Yep.
And then very importantly, after you've selected a set of negative controls and everybody agrees on what those negative controls should be included, you don't then afterwards, after you've executed your analysis against the negative controls, get to look at the estimates that they produce and then post hoc rationalize why, oh, well, that might not have been a good one. Because there's a temptation to then look and say, oh, well, that shouldn't be there, but it is. It's probably because it was bad. And that is a pretty critical piece. It's once you all agree on it, that's your set.
But now that I think a little bit more about your example, actually, if they'd done a proper analysis, even if infectious mononucleosis were to cause a concussion, for example, because you fall asleep or whatever, why didn't they adjust for that correctly? That would have been a confounder. So they could have just restricted to people who didn't have infectious mononucleosis and then established whether or not concussion causes multiple sclerosis. So just because they might be associated, that's actually not a bad thing for negative control, but you don't want a direct causal link between the two.
And when we say pathway, it goes mononucleosis, tonsillectomy, multiple sclerosis. The tonsillectomy, the MS is not, there's mononucleosis isn't on the path there. It was a precursor.
Yep.
So it wasn't on the path, and that would be okay.
Yeah. So had they used our approach to propensity scores, actually that would not have been a problem, because the propensity score would probably observe that infectious mononucleosis increases the risk of concussion. It would adjust for that, and so we wouldn't observe a effect for concussion. I mean, our approach would have been able to handle that, and apparently theirs didn't.
Yeah.
When you're selecting negative controls, do you need to worry about how frequent the thing is? Like, for example, if you choose some rare disease, you're gonna sort of artificially get a low correlation.
Well, not maybe a low correlation, but just a lot of uncertainty.
Yeah.
So the question is, how do you select negative controls? And I don't actually think we currently have that in our presentation, but I can briefly walk you through it, because we've actually developed a procedure for it, which happens to be described in the book of Odyssey. So the procedure that we usually use is, we actually have a system in place that's currently called the Common Evidence Model, that we pre-extracted information from the literature, from the product labels, and from spontaneous reporting. And we use that common evidence model, the knowledge that's stored in there, to already give you a candidate list. So if you have a specific outcome, multiple sclerosis, you can ask, give me all known exposures that have no evidence in these databases, data sources, linking them to multiple sclerosis, and you get your candidate list, which may have still many things that are wrong. If the expert looks at it, they might still eliminate things. So then you have to manually review that candidate list, and the way that we do that is we usually sort them by prevalence, because the ones that are most prevalent are usually the ones that are most interesting, because they give you the most precise answer on whether or not there's bias. So the procedure is use the common evidence model to generate the candidate list, and then manually review in order of prevalence, going from the highest prevalence to lower prevalence. And so the recommendation that we have is that you usually have somewhere between 50 to 100 negative controls in a study. So you just basically keep on going down the list until you reach that number. All right.
Yeah. So now we're going to look at so how we can use a negative control to detect if there is confounding or bias in your study, and see methods that the reasoning behind it, and see methods that we don't use, and then see how this reasoning can be fit in, and to actually how things are done in OHDSI. So negative controls can be divided into two separate classes. We have negative control outcomes and negative control exposures. So here we have a diagram, a structure of an ideal negative control outcome. So this one should be N, and the rest of the structure is the same as before. So we want to assess the effect of treatment A on outcome Y. Then we have a set of measured confounders L, and then a set of unmeasured confounders U. So the perfect negative control for outcome for this case would be an outcome that we know is not causally associated with treatment A, and the confounding structure that confounds A and Y is the same as the structure that confounds A with N. So in this case, and because we know that there is no association between N, a causal effect of A to N, and then this we know is a very hard statement, a very concrete statement to make. So because we know that, if we find an association between A and N, then we are sure that this is due to confounding and not due to a true effect. Yeah.
Explain a little bit of like, I'm having problem trying to follow the DAG with what the letters represent. So like, I know that N is a negative control. A would be exposure, Y is outcome, U are measurable, and then L is like predisposing criteria that you can exposure. Like, what would L be in this scenario?
So L in this case is just a measured confounder.
Yeah.
It's just
Yeah, it's C from before. Yeah.
it's like age could be there.
Yeah.
So confound. Oh, please.
Yeah, so it confounds A and Y, right?
So L is the exposure. L is exposure, A is the confounder,
No, A is the exposure.
and L is confounding A. Okay. And then U is the unmeasured. Okay, and then N, conditional
Yep.
measured. Okay.
That's a great description, actually. I was always looking for one in the figure. Basically, an ideal negative control is that thing that has the same arrows going into it as the outcome does, except for the thing that you're studying, in this case, A. So we're trying to understand A's effect on Y. A perfect negative control has the same arrows going into the Y, except for the A. So as you can see here, going into N, we have U going into N, L goes into N, okay? And going into Y, we have U, L, but also A. But that's okay for the A. And again, in control, we want to see the same things contributing to the impact on N, except for A. We don't want to
Except
see
for the
A.
exposure. So
Right,
then
that for the
you really
exposure.
identify that the exposure is causal. Okay.
Right.
Yeah, so if we see an association between A and N, then we should know for sure that this is driven this way, not this way. So there's no causal pathway going from this there, and then for sure there is a confounding issue here that's driving this association to be found. Yeah, and then a very similar thing when we want to. Oh, yeah, sorry. So, yeah, when we look at the. So, when we are considering a perfect and an ideal negative control outcome, we don't need the association. We don't need L to be confounding A and N, because this is if we assume that we took enough care to account for our measured confounding, then in theory we don't need L to be a confounding factor of the association of A and N. But in practice, that's very hard to do, right? So we need to find an outcome that we know is not associated with any of the measured confounders, but is associated with unmeasured ones. So yeah. So going back to negative control exposures, the perfect negative control exposure would be a very similar thing. So a negative control exposure would be an exposure that we know is not causally associated with Y, the outcome, but that the confounding structure that confounds the association of A with Y is the same structure that confounds the association of treatment B to the outcome Y. So again, if we in our analysis see that if we see that there is a significant difference, the significant effect of treatment B to Y, of our negative control to the outcome, then we can say that we have detected that there is some sort of a residual bias going on that drives this association. The issue with this structure here is that you need to have a lot of faith on what you are saying here is actually the truth, because there could be some sort of unmeasured confounding that confounds B with Y, but not A with Y. And then in this way, you would be, there could be a perfect association, there would be a causal association of F and Y, but you're missing it because you're thinking that it's due to a residual confounding while there was an unmeasured factor that was driving the association. So B was not actually a negative control, right? I don't know if this was clear enough.
Well, let me briefly jump in here. So there are two schools of thoughts on negative controls. And so one is being presented here, mainly the work by Eric Chechen, where Eric is arguing this point that you need to find the perfect negative control, which is, as Alex explained, is the thing that has the same confounding structure as the thing that you're interested in, but just doesn't have the direct causal relationship. And although we perfectly agree with Eric that that would be the perfect negative control, and so Eric usually just uses one negative control, there are two problems with what he's saying. One is, how do you know all that? How do you know all those arrows? How do you know that it has exactly the same unmeasured confounding as my question of interest? I think it's, I don't know, I see this quite often. It's especially, clinicians that tend to think that they know everything. But you don't. The real world is very complicated, and especially it has these annoying things called humans in them, and they make all these decisions that make all these arrows very complicated. Second, even if you knew everything, the probability that such a thing as the perfect negative control that it exists is very low, because it has to have all these same arrows, same dependencies, but not the direct causal relationship, and you have to know that for sure that causal relationship doesn't exist. So for those two reasons, we try to adopt a different approach in where we just select a very large sample of negative controls. Like I said, usually somewhere between 50 to 100, where at least we're sure that they don't have that relationship, causal relationship with the outcome or with the exposure. And where, because we simply have a lot of them, we'll be sampling from a lot of different types of confounding that exists, both unmeasured and measured. And so that's a different way of using negative controls the assumption there, of course, is that you're sampling from some sort of a distribution of confounding that exists, and that is exchangeable with the confounding of your hypothesis of interest.
Usually when they say unmeasurable confounding, is it because we don't have that data point, like let's stage in the claims database or something?
Exactly, yeah. So unmeasured confounding.
It's more complicated than that because we know of that variable and it's not measured or it's not in the data. There are other ones that are unknowns or whatever. Is that what you're saying?
Yeah, so it's very hard to think about what are actual confounders, both measured and unmeasured. And you usually will be surprised what actually ends up being associated with the exposure and the outcome. And so we just basically throw in everything, and you will find quite often that the things that pop up that, for example, are predictive of exposure are not the things that you thought of. So actually have this paper led by Rachel Weinstein that I also mentioned yesterday, where we compared our automated approach to propensity scores to a manual approach. And so we just looked at all studies done in the past that used propensity scores for that question, and we just used all their variables. And what we see is that our automated approach adjusts for all those variables just fine as well, but also a lot of other things that they don't adjust for. And there, if you start to look at them, you start to wonder, well, I could make an argument that it's actually a confounder. And so, yeah, you can think real hard, but you're not going to maybe think of everything that happens in the real world. So that's why we like to use a data-driven approach where possible. And the same with the negative controls. Yeah.
Would you also kind of suggest that even though you have 100 or 50, they should have a sort of a different category of negative control to have the different confounding influences? For example, if you picked 50 and they all dealt with back pain, you might have 50 negative controls, but they're all circulating around this notion of what back pain confounders would be involved.
Yeah, so good point. So when selecting negative controls, is underlying issue that you do have to think about is exchangeability with the question of interest. But also, like I said, we try to explain we're trying to create a sample of negative controls here. And if you're just sampling in one specific area, then you're not going to get a very good estimate of the actual distribution of confounding. So certainly things that are directly related, you shouldn't do. Like you shouldn't, if you have your negative control is ingrown toenail, then you shouldn't also include ingrown nail in general, because those are like 100% correlated. So pick one of the two, and then try and identify other negative controls that are dissimilar from the ones that you already have. Yep. Sorry. Oh.
Since the OHDSI system sort of treats the definition of outcomes and exposures all under this framework of defining cohorts, is it possible to define negative control exposures with as much ease as you would negative control outcomes?
Yeah, so you can define exposures or outcomes. It usually depends, or it makes most sense to pick the ones that fit the design that you're using. So if you're doing a comparative cohort analysis, sure, you could come up with negative control exposures, but that becomes really hard to implement in your study. And it's much easier to think of negative control outcomes. So you just keep the same T and C and just swap in other outcomes. That's much easier than when you try to think of, oh, if I use negative control exposures, then now all of a sudden I have to think about, are those negative control exposures comparable? I have to refit my propensity scores and all that. Whereas if I look at the outcome, negative control outcomes, that's a lot easier. But the opposite is true if I'm doing a case control study, and exposures is a lot easier. Yeah.
So, but the figure on the right is talking about negative control exposures. So what circumstances would you use negative control? How do you, I don't even know if I have my mind wrapped around what negative control exposure is, because I tend to want to lean into all those examples that we talked about before, where we're controlling the experiment of a drug of interest with a target group. But that's it. Those might have the intended outcome that we're looking at, just at a differential rate. So what would be an example of negative control exposure that we could consider? What example paper do you have of negative control?
Also, so the one that Alex showed just before actually shows you negative control exposures.
I thought it was negative control outcomes.
No, so these are the question is whether these childhood diseases cause that, and then we look at these exposures, although a broken arm in another study would be the outcome, but in this case it's a question whether that exposure causes multiple sclerosis.
Another example for negative control exposure is when you're using different study designs, like in a self-controlled case series where you include nothing but cases in your analysis and you want to see whether there's any bias there. You could then use multiple negative control exposures, but always analyze the same case population. So that's an instance where there's some intuitive ease in using exposure controls rather than outcome controls.
Yeah, so we talked most about these things. Yeah, so the last part is what Martijn said. So we need to think very carefully about what our negative controls are, and we still may get it wrong. So this is another paper in a viewpoint that was published in JAMA, and again it speaks in favor of using negative control. So they define them as we did before, and we should So it's the same thing all over again. So we need to be certain on the structure that we are using, so we need to be able to, we have to consult with people that can actually know how the structure, this causal structure, what this looks like, and they should, that we should use 3 or 4 more highly good ones.
Using negative controls count as multiple testing?
No, because you're not testing any hypothesis there. In fact, so what we do, if, for simplicity's sake, we include 100 negative controls, then you should expect 5% of them to be statistically significant at 0.05, because you're doing 100 tests, if you will, if you're looking at the p-value. So we're not multiple testing in that sense. We actually expect to falsely reject, if you will, the p-value at a certain rate, but only as that should be calibrated. So what we observe actually quite often, if you include 100 negative controls, that you reject the null hypothesis way more often than the 5% that you should see.
Yeah, but this in the case where in your approach where you use 100 negative controls, or here that you only use one or two, then okay, there is no multiple testing there, I think. Just test this association. Yes, so another paper by
Eric Chetchen.
So here you can. The main thing about this paper is that he advocates the use of negative control outcomes not only to detect but also to correct our estimates. And this moves one step further from the previous approaches that we just used to detect if there is some sort of unmeasured confounding. So yeah, the specifics are a bit complicated, but if you want to read this paper, then this should be a very nice read, I think.
I think you can maybe skip ahead to the calibration. No, yeah, that one. Oh,
This
yep.
one?
No, one further.
Oh.
Yep.
Yes, so have a look at what we're actually doing here. So using the approach that Martijn spoke before, so we maybe I need to start a step further before. So when we are doing in a randomized trial, what we want to do is we want to see if there is an effect of treatment to the outcome, right? So what we do is we gather our data and then we do some sort of statistical testing in order to see if there is a significant difference between the two treatment arms. And then we get this p-value, where what this p-value actually describes is the probability of observing observing something as at least as extreme as the thing that we actually calculate from our data. And in a randomized trial where there is no systematic error, then we expect that the null distribution of these observations would be centered around 0. So we expect that if we were to repeat this type of analysis again and again and again, then there was truly no effect of the treatment to the outcome, then we would see that our calculated our estimates would gather around 0. But this is not the case in an observational study, right? So in this case, if we did this thing again and again, then we would see that our estimates would concentrate around a biased value that is different from 0. So in order to be able to correct our initial, so statistical testing, what it does, it only takes into account the statistical error that can be present in our data and not the systematic error. And so what the approach that Martijn actually described before, where we have identified like 100 or more negative controls and estimate the effects from the data using the same procedure as we did for our own estimate of interest, then we would be able to empirically represent the null distribution inside our own data set. And then this null distribution would take into account the presence of systematic error or selection bias or all these types of error. And then we can use this new empirical null distribution to correct our p-values account for the systematic error in our data set. And so you can see here, so in the first graph, so we have a set of several negative control exposures in this case. And the dashed lines represent the significance boundaries of at 5%. At the 5%, if we were to use the regular statistical approach. So in this case, we would expect that our negative controls, we would find a significant result at 5% of the times, right? Because if we're testing multiple times, then we expect that 5% of the time we're wrong. But in this case, because there is still a systematic error in our analysis, that we see that in this case, many of the results fall below this cutoff. So here we have significant results and then above here. So we would expect that the majority of our results would be non-significant because we know that there is no association because these are negative controls. And then here we would have just the 5%. But the truth is that we see a lot more. And then if we use our calibrated p-value cutoff, then we move our null distribution. So we move our null distribution to account for the systematic error in our data. And then we see that in that case, only one of these negative controls is actually found to be significant. I don't know if you want to say something about this graph. So
maybe we'll go to the next one. That's
yeah. So so the natural next step would be to use this type of approaches to actually not just calibrate our p-values, but also calibrate our confidence intervals around our estimates, so to make sure that we correct also for unmeasured or residual confounding in our data. That would be it.
Can you go one further? Yeah. So this is actually an example where we apply this confidence interval calibration. And what's interesting here is that this is the Graham paper that we just reviewed. So what we did is, in this analysis, is we reproduced the Graham paper in our own data, and we didn't have as big a database as they had, so we had a slightly bigger confidence interval, but we pretty much replicated what Graham did in our data. But there was another paper by almost the same people that did the Graham paper a while back, where they, led by Southworth, where they did the same analysis, but they didn't do any adjustment for confounding. And that's actually, he got a lot of grief over that paper. And so in that paper, instead of a harmful effect for this outcome, they found a very strong protective effect. And so we replicated that paper, didn't actually find such an extreme effect, but still also very strong protective effect. And then we applied this idea of confidence interval calibration. So we added a lot of negative controls, and we showed actually that because they're not adjusting for confounding, you have a lot of bias. And what that does is, if you then include that information in your empirical calibration, your confidence interval just basically blows up. And so we were able to show that this rather stupid study had a lot of bias and therefore gets a very wide calibrated confidence interval, whereas the proper study, if you will, the one that we were just reviewing, the confidence interval calibration actually doesn't do anything because there was hardly any bias observed using the negative controls. So that's the nice thing about this calibration procedure. And whereas before these two studies were very much in disagreement, we're still not completely agreeing, but at least the confidence intervals started to overlap, mostly because we had to blow up that one for all the bias that was there. All right. No. Thanks. So we're at the time of the lunch break. So, let me hear your thoughts. What are the threats to validity in Graham's paper?
Publication bias.
Publication bias. Yeah, maybe.
They had a bunch of negative results that they didn't.
I'm sorry, they had a bunch of negative controls?
Is that publication bias?
Yes, yeah.
They mentioned confounding for factors not adjusted for, and confounding by estimated factors.
So, sorry, confounding by things that they didn't adjust for and confounding by things that were not measured, right? All right. Yeah, so I mean, this is a observational study where we're doing this comparative cohort analysis, where we're comparing two groups where the real question, of course, the real fundamental assumption here is that they've achieved balance or made those two groups comparable enough to actually draw causal inference. That's the big question, that whether they'd actually achieve that, right? I mean, we're comparing people that are taking this new drug, the Bigotron, and we're comparing them to people that are on warfarin, which is an older, cheaper drug. And so who's to say that the people that take that newer drug are actually going to be comparable to the older group? So what do they do to mitigate that risk? What's their strategy for making those two groups comparable? Yep, propensity score matching. So they have a what they call a extended number of covariates that they include in their propensity model. I think those are the same that are in, what's this called, table 1. And so these are variables. They put them in the propensity model, they compute a propensity score, and then they match on the propensity score with the assumption that that actually makes the group comparable. So how do we know that they succeeded in this strategy, that they made them comparable? What's their own diagnostic that they use for this? Yep, standardized difference of means. So they look at whether or not those 70 covariates that they put in the model end up being balanced after they adjust for or match on the propensity score. And did they achieve that?
Yeah.
What?
They didn't show, we were talking here, they didn't show what was the standardized difference prior to.
Yep, I always find that an interesting question. What did these groups differ on before they made them comparable? They only showed a standardized difference of mean after matching, and they somewhere declared that their cutoff, I think, was 0.1, and none of the variables are below 0.1.
Martijn, on that point about the before and after, for purposes of the estimate that they're performing, is it safe to say if they have a population imbalance, their estimate will be relatively free of that type of bias? But you lose generalizability if you are basically saying, in order to get to that balanced population, we needed to throw away so many people from the before population, before matching. Is that the implication here? It didn't affect their effect estimate. Did it affect my question to you is, does that affect the effect estimate, the fact that they had to throw away so many people to get to a balanced population?
Yeah, so what did they need to do to make the two groups comparable? How many people did they lose? And I don't think they're very explicit about that, but there's, of course, then the real danger that the thing that you're estimating is only valid in the population that ended up in your analysis, and it's hard to generalize that to the population beyond. And so Jamie pointed out that, well, from the target group, I think they use pretty much everybody, but they certainly lose like 200,000 people in the comparator group. But maybe in this case, they didn't actually care about the comparator group too much. They just wanted to compare the Bigotron to some alternative. But that is an important thing to look at. And certainly if they showed how much they differed before the matching, you could at least get a little bit of an idea of what they had to do to make them comparable. So does that mean that we're completely confident that all confounding is now gone? I see Mark nodding his head. Yes. Well, they themselves are a bit careful about that in the limitations section. So what do they say? Oh yeah, you actually saw it. Already said it. Sorry. There might be things that they didn't adjust for that were actually confounders. There might actually be things they didn't adjust for simply because it wasn't measured in the data. But we don't know. They went to the strategy of just acknowledging this limitation in their paper, and then that's it. Which is not what we do. We like to use the negative controls. Yeah, we went through that. So another threat to the validity would be measurement error. what did Graham say about that? Specifically about the outcome.
86 to 97.
Yeah, they have this nice, I think I have it in my slide as well, they have this nice quote, they reference this other paper, a positive predictive value of 88 to 95%. They cite these papers, so these papers, didn't have time to look at them, but did they measure this in this particular database, the Medicare database? No, at least one of them was in a Medicaid database, so I find it quite a large leap of faith to assume that that performance actually translates to this database, but that's just me. So positive predictive value tells you of the people that were identified by their outcome algorithm, how many of them actually had the outcome. But I would actually also like to know sensitivity and specificity.
Does a fee evaluator give you at least some of that?
Yep, so fee evaluator would compute all of those metrics for you. Yep. Has some other limitations, but at least you get an estimate of the sensitivity. And the reason why I tend to worry about other things than positive predictive value is like sensitivity could be 1% or 2% or very low. And it could actually be 10% in the Debickerton group and 100% in the warfarin group, and that would completely bias our results. So I'm not too impressed by this metric. But anyway, that's what they presented. So what we would do in this case...
Most observational study does not include this at all.
Yep, good point.
Because we do a lot of natural language processing, we all the time have to justify why what the operating characteristics of the NLP might be. But all of our sponsors just ignore the fact that due to an ICD there's limitations. So
Yeah.
I think at least this is one positive step in the right direction.
I don't know, I would push back and say positive value could give you a misleading interpretation of what that, to your point about what was the real sensitivity. So if you feel good about that number, and then Martine told you yes, but the sensitivity was 3%, would you feel as good about that number anymore?
Yeah, but I guess what I'm trying to say is at least the study team is looking at some metrics. How would you go about trying to figure out sensitivity in the Medicare population?
Evaluator.
Sorry, which was introduced yesterday.
Oh, you're right. I mean, at least we have now some confidence that the positive predictive value isn't 1%. I still don't know how much it transfers between the databases that this was measured in. And as we mentioned before, actually, if you look at those papers, the papers explicitly say not to do what they did here, but that's a side point. So what we would do differently in this study, except maybe apply fee evaluator now that we have it, is we would include negative and maybe positive controls. And so actually we did that. And so just briefly showing what we actually found when we did that. So we have negative controls where the true effect size is 1, and then we actually have this automated procedure where we can artificially turn negative controls into positive controls with larger than 1 effect sizes. I'm not going to go into how we did that. But you do see that if we apply the Graham design, so each one of these dots is a negative control. So hazard ratio that way, standard error that way. 88% of the negative controls included 1 in their confidence interval. And of course, if it was completely unbiased, this design, it would be 95%. So there was a little bit of bias, but actually this is not as bad as I've seen it, certainly. So it's a pretty unbiased study in that sense. So this actually tells us that maybe missing those covariates that they were worried about is not as bad, can't be that bad, because we don't see that much bias after we adjust for the ones that they did include. All right, any questions about this and threats to validity? All right, then it's time for Jamie.